Hi, our first speaker today is Simona. She's a fourth-year PhD student at the University of Leicester, working with the instrument team on SXI on board SMILE. Her PhD focuses on the variability of X-ray emission in Earth's exosphere. This involves analysing data from XMM-Newton and simulating future SXI observations. Before her PhD, she completed an undergraduate degree in aerospace engineering at the University of Pisa, and then moved to Moscow to do a master's in space engineering. I'll let Simona introduce her talk and take it away from here.
Thank you very much, Gemma. Good morning, everyone. I am Simona, as Gemma said. I am a final year PhD student at the University of Leicester. And my PhD is about studying the interaction between the solar wind and the neutral particles from the outer atmosphere, and in particular the X-ray emission that comes out of this interaction. For today's presentation, I'll be talking about one of the storms from October 2024. And I chose October 2024 because it was an extremely active period for the sun. We had a number of CMEs, coronal mass ejections, being released from the sun. And here in this simulation here that I put on the first slide, I'm just showing like an example of two CMEs that were released in the early October. This was like the 3rd of October 2024, and we had two consecutive CMEs being released from the sun in the middle, and then we can see this propagation of the solar wind up to Earth, which is this yellow dot. A CME is characterized by a strong magnetic field that is attached at the sun at both ends. This is called a magnetic cloud or magnetic obstacle as well. And ahead of it, we have a turbulent sheath, which is a region with compressed solar wind plasma that cannot go around the magnetic obstacle, so it piles up, it accumulates in front of it. On the right-hand side, I put the time series of the solar wind speed, and then interplanetary magnetic field, temperature, solar wind proton pressure, and finally at the bottom we have the CMH index, which is a geomagnetic index that represents the geomagnetic activity at Earth. These gray shaded areas, they are the magnetic obstacle periods, and they are preceded by a white area enclosed between two vertical dashed lines, and they represent the ICME sheath. So we can see that in this period that goes from the 6th of October 2024 to the 12th of October. So in these 6 days, we have first 3 ICMEs that caused a moderate storm. So the CMH index goes down to minus 150 nanotesla. And then a few days later, we have one single ICME that causes a severe storm with a CMH index going down to minus 350 nanotesla. So that was one of the strongest storm of, actually the second strongest storm of the last 2 solar cycles. So it was quite an important one. Now, whenever we have the solar wind approaching Earth, it doesn't come just with protons. It also brings highly ionized heavy ions like oxygen 8+, carbon 6+. These heavy ions, they interact with the exosphere, which is the outermost layer of the Earth's atmosphere. It goes from approximately 500 kilometers of altitude to beyond the moon's orbit, and it's mainly made out of neutral hydrogen. Now, these heavy ions, they interact with hydrogen, and because of the collision, we have electron transfer from the neutral particle to the ion. And because of the relaxation of the electron to a lower energy state, then we have the release of a photon in the soft X-ray band. Now, because the heavy ions cannot penetrate directly into the magnetosphere, then they pile up around the magnetopause in a region called the magnetosheath. So the magnetosheath is the region where we have the strongest X-ray emission because of this phenomenon called solar wind charge exchange, or SWCX in brief. This is the main principle behind SMILE. SMILE is the Solar Wind Magnetosphere Ionosphere Link Explorer. It is an ESA mission jointly made with the Chinese Academy of Sciences, and it will launch in 2 weeks from today, on the 19th of May. It carries two remote sensing instruments, which are the soft X-ray imager, a wide field of view X-ray telescope that will observe the X-ray emission from the magnetosheath in order to find the dynamics of the magnetopause. And it also carries the ultraviolet imager, which is a second remote sensing telescope that will observe the northern hemisphere in order to catch the auroral emission from there. So SMILE will be the first mission that will observe at the same time the movements, the dynamics of the magnetopause, and the resulting auroral emission from the northern hemisphere. It also carries two in situ instruments, which are LIA, the light ion analyzer, and MAG, a magnetometer, in order to understand the local solar wind features. Here we can see a simulation of the X-ray emission coming from the magnetosheath. This is made using an MHD model. We can see this brightest bit in the middle here, and that corresponds to the magnetopause. So that's one of the main goals of SMILE, understanding the dynamics of the magnetopause using these wide field of view observations of the magnetosheath. So this is a simulation done with an MHD approach, and this is what the same simulation looks like as observed by SMILE. So it might look a little bit different, but the information behind it is still retained. So we can see that the brightest bit is here in the middle, and if we look at the distribution, the histogram of the intensity of these pixels, then we can see that this distribution here, for example, on the x-axis, it replicates the one that we've seen before, with the peak being pretty much in the same location. So that corresponds to the magnetopause location. However, there are people from the SMILE modeling working group, which have been working on developing a tool to understand the future SMILE observations in different solar wind situations. However, SMILE is not going to see the magnetopause location. So it can also be used to indirectly probe the solar wind heavy ion composition and the exospheric neutral density. So that's because the SWCX emission, so the X-ray emission from the magnetosheath, is caused by these two elements. So we can indirectly analyze them. And this is very important because since 2011, we haven't got any reliable measurements of the solar wind heavy ion composition because of a hardware problem of the spectrometer on board ACE at L1. And also regarding the exospheric neutral density, we don't have any in situ measurements of this neutral population. So doing this indirect analysis is extremely useful. However, SMILE hasn't launched yet. So we need to find alternative ways to understand whether our theories about the SWCX emission make sense. So for my analysis, I've been using XMM-Newton, which is another X-ray telescope that can observe the SWCX emission, but it does it only serendipitously, whenever the geometry of the observation allows it. So here in this schematic, we can see the magnetosheath being this bright bit outside of the magnetosphere. And then this is XMM-Newton and its highly elliptical orbit that goes below the ecliptic plane. So sometimes XMM-Newton, when it is looking at its astrophysical target, its line of sight can bisect the magnetosheath, so we can catch X-rays from there. But the line of sight of XMM is extremely narrow. It's at 0.5 degrees by 0.5. So it's called a pencil beam, and it can just it can sweep through the magnetosheath, but it cannot catch the global dynamics of the magnetopause, just like SMILE would do. So if we want to compare SMILE with XMM, SMILE has this 26 by 15 degrees of field of view, and the XMM has a 0.5 by 0.5. So it corresponds to one of these teeny tiny pixels in the SMILE field of view. So XMM has got a few limitations, but that's also why we are launching SMILE, to overcome these limitations and understand the dynamics, the global dynamics of the magnetosphere. Now, coming back to October 2024, what I did was understanding checking whether we had any usable XMM observation in this period that goes from the 6th to the 12th of October 2024. And it turns out there is one single XMM observation that is actually usable, and it happens during the main phase of the first storm, of this moderate storm, and it covers the sheath of the second ICME and the magnetic obstacle of the second ICME. So it might sound a little bit like a bummer because we just missed one of the strongest storms of the last 2 solar cycles. However, we should consider ourselves quite lucky because usually whenever we have a strong radiation from the sun, so especially during ICMEs, XMM-Newton goes into safe mode. So we can't use its data, and that's pretty much what happened during the second storm. But it didn't happen during the first one because even though it's a moderate storm, so the radiation is quite important, XMM was located at the flank of the magnetosheath, so it didn't get affected too much by the direct solar radiation. Also, this observation lasts for 18 hours, so we have 18 hours of continuous coverage of X-ray photons, and also it doesn't have any, XMM was not observing at any extended sources. So this is on the right-hand side, we can see how the XMM observation looks like. It's got this very small, they are called point sources, because during that period, XMM was observing a cluster of stars. So they look like, they look like point sources, and they are very easy to remove. We just like all these green ellipses, they represent the location of the point sources that we removed from the observation. So this observation represents a very, very good opportunity to see how SWCX models they work, especially during severe conditions of the solar wind. So what we did was simulating the solar wind charge exchange emission during that period. Here in this plot, I'm showing the solar wind pressure, temperature, and CMH index, just like before. And then at the bottom, I'm showing the XMM count rate. So this is the number of photons per second in black. And we can see that XMM has got a first peak, it's showing a first peak of this SWCX emission during the sheath of the ICME. So this is when we have a peak of the solar wind pressure because of how compressed the solar wind is in front of the magnetic obstacle. So this peak is somewhat replicated by the model. This model is an MHD model. So it's purely MHD. It's based on this equation called the Craven's equation, which is widely used in the literature. And it estimates the solar wind charge exchange emission as proportional to the exospheric density and the solar wind proton density and velocity. And then we have this alpha parameter here, which is a factor that includes the amount of heavy ions in the solar wind and the efficiency of the charge exchange. So in this first model, I'm considering a constant alpha, so a constant value for the heavy ions in the solar wind, a constant hydrogen density from the exosphere, and then I'm allowing only the solar wind velocity and density to change. So this is something that is widely done in the papers working on the solar wind charge exchange emission, and also in simulating the SMILE data. So we usually go for simulations of the SWCX emission that consider only the solar wind proton density and velocity to vary. So in this model, which is an MHD-based model, we have the first peak of the SWCX emission that is somewhat replicated in the model. So we can see a little peak in this purple curve. But then the second peak that is the XMM data is completely missed by the model. And that's because it's an MHD model, so it can see somewhat the pressure pulse that we have in the ICME sheath, but the second peak that happens while the solar wind pressure is steady and low is completely missed. So the fact that we have this big gap between the model and the observation could be caused by the exospheric model being constant, and also we use a spherically symmetrical model. So it might be that there are like some asymmetries along the line of sight, and also we're using an alpha factor. So the one that includes the heavy ion abundances, we're using a constant in the first model. So we should consider these two parameters and how their effect changes the solar wind charge exchange model. So first we consider a new exospheric model. This is a very a state-of-the-art model of the exosphere. Is done by a research group from Goddard, NASA, and it relies on the neutral hydrogen density and temperature from the WACMX model of the thermosphere. So they use these values and they consider gravitational forces, Coriolis forces, and solar irradiance to understand how the exospheric density works at different altitudes. So in this last plot here, we can see the exospheric density at 10 Earth radii across time, and we can see that it steadily increases from the 6th to the 11th. However, this increase is very minor. We only have it goes from 49 to approximately 50 cubic centimeters over 3 days. So it's a very negligible increase. However, this value is almost twice the one that we used at the beginning. So in this way, the new model, the one that incorporates both MHD-based results and the new mate model, it decreases the gap between the model and the observation when we compare it with the one that we used before. However, this second peak, again, is completely missed, and that's because the exospheric model that we used is not observing any variability. So it might be that this variability is coming by solar wind compositional changes in the heavy ion population. And in order to check that, we extracted the XMM spectra of during the time of the ICME sheath passage and during the time of the magnetic obstacle. So we extracted these two spectra from our XMM observation. And so the spectra corresponds to these black crosses, and we fitted it with our spectral model that includes the cosmic background, includes instrumental component. But what we are seeing here with these colored lines is the SWCX model. So every single line corresponds to, well, we call it line because it's a line emission, but then it looks more like a Gaussian when it's when the model is folded through the instrumental response of the XMM telescope. So we have all these Gaussians that represents the line emission of each ion, And the different colors represent different ions involved in the solar wind charge exchange process. So for example, the red one is oxygen 7, and then we have the blue one, which is oxygen 8. And then if we compare these two periods, then we can see that the main difference is in the oxygen 8 line, which is almost 3 times higher than during the sheath. Also, we can see some difference here in the neon 10 plus line. So we have a difference. There is an increase in the emission of particular ions. In particular, they are fully ionized heavy ions. So this can be considered as a proof that there is a compositional changes going from the ICME sheath to the magnetic obstacle. Now, before 2011, we could use ACE data to get the heavy ion abundances to use in our SWCX calculations. But because of a hardware anomaly, the data set is much limited now. But very recently, a group of researchers from France, they developed some empirical formula to use the ACE data set to get the heavy ion densities. And in this way, we can recalculate the alpha factor. So the one that we used at the beginning was a constant alpha factor, which I'm showing here in the bottom plot as a purple line. And then we recalculated this alpha factor using this empirical formula recently obtained by Kutrumpa last year. And we can see this new alpha, it varies in time, and it can see a peak during the peak that we also see in the SWCX emission. So this is a proof that there is a compositional change that can be observed also with this newly developed empirical formula. However, when we use this new alpha in the model, the peak is still underestimated. However, the model to observation gap decreases. So we saw spectrally that there is a compositional variation. We saw it with this newly calculated alpha that there is a compositional variation, and it is very important to consider it because using simple MHD models is not enough. However, what will actually be beneficial is a new mission that monitors the solar wind heavy ion composition around our planet. So that's why I've been involved also in the ELFIN mission, which is a CubeSat, a 16-unit CubeSat that will orbit around our planet on a 12 RE orbit, and it will measure the heavy ion abundances all around this circular orbit, both in the solar wind and in the magnetosheath, and also at the back of the planet in the cold dense plasma sheath to see how that originates as well. It will carry 2 instruments, which are TFIPS, which is a solar wind heavy ion spectrometer, and MAGIC, which is a magnetometer from Imperial College London. And it's been proposed by Jenny Carter at Leicester, and it got funded by the UKSA for a phase 0 that has ended in 2023, I think. And then it's running for the ESA Mini-F mission class. So this would be highly beneficial for SMILE analysis and also for SWCX-related analysis as well. So what we've seen so far is that we had an XMM observation happening during a main phase of an ICME-driven storm. We tried to simulate it using a simple MHD model, but there was a big model to observation gap. The first peak was somewhat observed due to the peak that was also observed in the solar wind proton pressure. However, we needed an extra component due to the solar wind heavy ion variation in order to decrease the model to gap discrepancy during the second half of the observation when we have this higher peak. So it's very important to consider heavy ions in our SWCX analysis, and yeah, and this is what we understood from this analysis. And that's all. Thank you.